Hello and welcome to Equilibrium Part 1. Just some information to read here. Really wanting you to understand that if lots of products are produced, we consider it product favored, which means the reaction they call it lies far to the right. If little products are being produced, then it says that the reaction lies far to the left, or it's reactant favored. Please go ahead and read through this, just some information to explain kind of what we mean by equilibrium and how these things are related. Pause if you need to. Continuing to read through this, pause if you need to. So here we're going to learn how to write an equilibrium constant. So it talks about a generic equation here where the lowercase letters are your mole coefficients and the capitals are your chemicals, either elements or compounds. To write an equilibrium expression, you're going to use a capital K, not lowercase, capital K. And then you're going to put the concentration, that's what square brackets means, remember. Concentration is moles over liters, of each of the products, or the product of the products. So I'm going to multiply product of the products. I'm going to multiply the concentration of C raised to its mole value times the concentration of D raised to its mole value all over the product of the reactants, so the concentration of A raised to its mole value times the concentration of B raised to its mole value. So for an example one, we're just going to practice writing an expression. So remember, we're going to put products on top, reactants on the bottom. So there we go, K equals. So I took the concentration of NO2 to the fourth, because it's fourth mole, 4 moles, H2O to the sixth, concentration of H2O to the sixth, over the reactants, so NH3 to the fourth power and O2 to the seventh power. So that's how you write an expression. For an example now, we're going to calculate the value of K. So first you'd want to write an expression. Okay, so we're going to start with writing the expression. Okay, and then you're going to substitute in numbers. But remember that these square brackets mean molarity. So that means you have to have moles over liters. And if you notice in the problem, I gave you volume and you're given moles of each. So I had to go over here and calculate the molarity, moles over liters, for each of these and then substitute them into their proper places. Down here, you want to be very careful on your calculators that you're doing this correctly. You probably may need to put this use more parentheses than I show here. I don't tend to use parentheses. I would take this if I was doing this problem, and I'd say 1.0 times 10 to the negative 2 times 1.0 times 10 to the negative 2. That, aka I'm squaring it. Divide by 1.4 to the negative fourth equals, divide by 1.4 to the negative fourth equals. So I did that twice like I squared it. Divide by 1.25 to the negative fifth. So again, you need to know how to use your calculator. So practice with your calculator to make sure you can get this answer using your calculator properly. Example number 3. So here we have this problem given. This really goes with A right here, and it wants us to calculate K for this reaction. So then we're going to calculate K for this version of the reaction and then this version of the reaction. So let's talk through that. Once you've calculated those, you will see these values, okay? And I want to compare those values to some patterns that you can see. So what you should have done, and maybe you need to pause and do that now, is calculate with the method I just showed you K for A, B, and C on your own paper. Welcome back. Ask yourself now, going from A to B, so looking at A and B, did I have to get from A to B forward or reverse it? One of the two. Either kept it forward or reversed it. And then the second question you're going to ask yourself is, what did I multiply by? So for A to B, to go from A to B, I had to reverse the reaction. So that means to write it in reverse, meaning I write the products first, then the reactants. And then you would have had to multiply by 1. It's important to, even though multiply by 1 seems kind of duh, you need to write that because you want to make sure you always remember these two things to ask yourself. Forward or reverse, what do I multiply by? Okay? And now if I can go over to C for just a moment. So if I'm looking at A to C, so looking at A, going to C, again, ask yourself the two questions. Forward or reverse, what do I multiply by? So we kept it forward. Reactants are on the same side as these reactants. But we had to multiply through by a half. I know that's the same thing as dividing by 2, but I would not let yourself talk in that language. I would always talk in terms of forward or reverse. What do I multiply by? Okay, now we're going to look at how we'd write the expressions different. So down here I wrote the expression for A. Remember, we're doing the product of the products raised to their mole coefficients over the product of the reactants raised to their coefficients, mole coefficients. That's what I did here. And what do you notice about those two? Okay, above are the expressions for A and B. So I want you just to look at those for a moment and think about what you notice about those two. You can say that to yourself. And also looking at A to C. So this is our expression for A, and this is our expression for C. So all I did was write the expressions for each of them and just put them side by side. Okay, so above are the expressions for A and B. Do you notice that A and B are reciprocals or the inverse of each other? Basically, they're flipped, right? I just flipped them. Find the reciprocal inverse button on your calculator, input the value of 3A, then notice that A and B are reciprocals of inverse of each other. So what I want you to do is I want to type in, this is a copy of two calculators I know most of you have. I want you to type in this, 3.8 times 10 to the 4th, okay, and then I want you to hit this button. If you have a Casio, you're going to look for x to the -1 button or 1 over x button. Those kind of buttons would, if you don't have the right, if you can't figure out the button, please email me and I'll help you. Okay, so once you do that, once you put A in and you hit the reciprocal button, you will get this answer. Similarly, if I look at A to C, hopefully you notice that going from A to C, you multiplied by 1/2. So everything was the same order. It wasn't flipped this time, but everything's multiplied by 1/2. So if I take 2 times 1/2, I get 1. If I take 1 times 1/2, I get 1/2. And I get 3 times 1/2, I get 3/2. So I want you then to input the value of 3A, then raise it to the multiplier, so the 1/2. For this example, 1/2. So you're going to find your caret key, or you might have a y to the x key, depending on your calculator. Again, if you cannot find the proper button to use, please email me with a picture of your calculator and I will help you. So once you take A and you raise it with the caret key or the y to the x key to the 1/2, you may have to put the 1/2 in a set of parentheses, depending on how you're putting that in. So if you don't get the answer of 1.9 times 10 to the second, try different things to understand how to properly put it into your calculator to get this number. All right, so from example 3, we can come up with some conclusions and some rules. So this is the generic expression. If I reverse the reaction, remember we talked about A and B were reverse of each other, reaction-wise. If I reverse the reaction, then I'm going to take the reciprocal of the original K, or whatever I know the K from. Okay, if I multiply the reaction by an n factor, okay, if I multiply the reaction by some n factor, then I'm going to take the K value for the one I multiplied by and raise it to that power. So those are some rules of equilibrium constants. Here are some other rules. Basically, you need to know that K is meaningless unless you have a balanced equation. This is that whole raising it to a power, whatever you multiply by. And then this is the reciprocal rule, where we know the forward and reverse reactions are reciprocals of each other. Okay, now the difference here is that you are going to, like we did similar in Hess's law, or like we did, well, similar to Hess's law. So when you have multiple reactions that you need to get an overall reaction for a K value for, instead of adding the new H's, we have K's this time, so instead of adding the delta H's, you're going to multiply your new K's. I will show you some examples coming soon here. This is a very big, important one right here. When you're writing expressions, or when you're figuring out the equilibrium expression, you leave out anything that is the liquid state or the solid state. So you leave out, don't even write them in your expression, they become a 1 if you have any liquids or solids in your expression. So states of matter are very important in this unit. You do need to know them. So here's an example of aqueous, right? There's a solid, an aqueous, and a gas. Remember I said solids and liquids are left out. Everything else should be in there. So basically gases and aqueuses will be in your expression. So this is just an example with having ions instead of atoms of how to write an expression. So here you go. These were included, okay? Now I didn't put in zinc because zinc's a solid, so zinc was left out. And it's a 1 basically. Hello. Okay, so for example 5, we are now going to use that product rule where we have an unknown equation, an unknown K for this equation, but we have a multi-step reaction, or two reactions that created this one, and we have Ks for these values. So what we're going to do is we're going to look at what we need and say, what do I do to A to get it look like my unknown? What do I do to B to make it look like my unknown? So let's begin. So I look at A and I say, remember there's two questions when we say, what do I need to do to A to look like my unknown? The two questions are, for to reverse, what do I multiply by? So we're going to need to reverse A, and we're going to need to multiply A by 1. Always consider, what do I multiply? So it's very similar to what we were doing just a few minutes ago. So I reversed A, and I multiply by 1. Let me show you. So I took this A and I reversed it. It means I flipped the reactants and the products around, and I multiplied through by 1. Then I look at B, and I say, what do I need to do to B to make it look like A? Excuse me. What do I need to do to B to make it look like my unknown? So we're going to keep it forward. Apologize for that. And we're going to multiply by 1. So that's what I did. There we go. Now you want to make sure things eliminate that should eliminate. So remember, if things are on the same side of the arrow, in all of your reactions, they will either sum or, they will sum. If things are on the opposite side of arrow, they will either cancel or reduce. So here, N2 and N2 in red are both 1 and 1, so they completely eliminate it. And so here, this O2 and this 2O2 leaves me just with 1 O2 left. So now I have 2 NO gases, and 1 O2 gas, because remember this went down to a 1, going to 2 NO2. So I have the equation I wanted to do. I have the equation I needed. Try not to avoid this. This is where you lose yourself and you don't realize you've made a mistake. So you really need to do this step. I know some of you try to just do it up here in your head and you lose yourself. I really encourage you to play this out, and I expect that in your homework. So now that I know I got the equation I wanted, I now need to apply the rules of equilibrium constants to my Ks. So here I took and I reversed the reaction. So when I reverse the reaction, I take the reciprocal. So I put my K under 1 and I get my answer. Make sure you know how to use your calculator to get these. Try it out, please. And then for B, I had kept it forward and multiplied by 1. So since I kept it forward, it was the same thing. So then I'm going to multiply my two values to get my total. Example 5B. So here I have a given equation, and I'm going to go through that process again. So that's the equation I'm trying to get. What am I going to do to A? I'm going to reverse it, multiply by 1. So I did that. What do I need to do to B? To make it look like my unknown to B, I need to reverse it and multiply by a third. Remember, we're going to talk about multiply by instead of what do I divide by. So there we go. Now we're going to see that things eliminate to get our unknown. As you can see, N2 and N2 cancel. O2 reduces. This 2 O2s, because of this O2 on the opposite side, reduces down to 1. So I do have 2 NOs, 1 oxygen, and 2 NO2s. So that's the equation I need. Now I need to apply the equilibrium constant rules to my K. Okay, so here I reverse multiply by 1. So here I put the reaction underneath 1, or the reciprocal. And then here I reversed and multiplied by a third. So I put it underneath 1, and I took it to the 1/3 power. I highly encourage you to do this part first and then hit the reciprocal key like we talked about before. You may need to put either this in parentheses or the 1/3 in parentheses when doing this. Again, you need to use your calculators. Make sure you know that you can get these two answers using your calculators. You got to know how to use your calculators to do these problems. So once I get my new values of K, I multiply those, I take the product of those values, and I get my final answer of K. All right, example 6. So in example 6, this one's a little different because I ask you to write the formula. So it says calculate the formation of 1 mole of NOBr. So this is what I'm trying to find K for from its elementals. So these are all diatomics. But you have to balance it. So we got to balance it. That's what I did here. And then I have to write it as it's requested. It's asking us to form, that means makes, 1 mole of NOBr. Right now I'm showing 2 moles of NOBr being made. So I'm going to multiply through by a half to get this into the proper requested amount of 1 mole, formation of 1 mole NOBr. Now we can apply the rules that we just learned a moment ago. And here they are. Okay. So again, I looked at A. What do I need to A? I had to reverse it, multiply by half. So I did that. To B, I had to keep it forward, multiplied by half. So I did that. I rewrote these, and then I said, okay, NO eliminates. I have 1/2 N2, 1/2 O2, 1/2 Br2 on the same side going to NOBr, so I have the formula I need. Now I can do what I need to do to my case. Remember, if we reverse it, we put it underneath 1, and I raised it, I multiplied by 1/2, so I have to raise it to 1/2. Remember, you're going to do this part first on the bottom and then take the reciprocal of it. Again, I can't emphasize enough, you need to make sure you can get my answers using your calculators. All right, so then for B, I had to just raise it to 1/2 power. I didn't reverse it, so that's why it's not underneath 1. Then I'm going to take the product or multiply my new values of K. All right, some more notes about the difference between heterogeneous and homogeneous. Okay, don't forget that you want to leave out liquids and solids into your expressions. They are just ones. We're going to look at how we can convert from concentration to pressure. This is a very lengthy explanation. For now, due to time, I'm just going to show you the formula. I will eventually explain it to you, maybe not this year due to what's going on around us in 2020, but for now, just know that there is a way that we can derive this. If you were here Friday before spring break, I did explain that. I'm not going to take the time to do that now. Okay, you don't need to know that anyway, so really, you just need to know the formula. Okay, so here we have an equation, and it's just showing that I can do Kp. Now, the P is important because, and that really should be a capital P. Let me fix that while I'm sitting here. Let's do that really quick. Sorry for this. Let me pause, and I'll come back. Okay, that's all fixed. So it should be Kp, and that means pressure. So the numbers you plug in here are going to be of pressure values. So atmospheres, millimeters of mercury, kilopascals, pounds per square inch, what am I missing? Torr. So any of those pressures could be plugged in here. They all should be the same unit, okay? And so it's the same concept, you know, provided these are gases or aqueouses, you can plug them into it. Same thing, you're going to put your product of your products raised to their mole values over the product of your reactants raised to their mole values. And the difference is that you'll be using pressure units. Please note that they are not the same thing as a square bracket. Square brackets means moles over liters. Pressures are a whole different unit. Okay, so the relationship between K and Kp, that long derivation that I showed you guys in school, if you were here this week before spring break, looks something like this. It gets you to this formula, the relationship between K and Kp. So Kp is equal to K times RT raised to the n value. Now, you're going to be given the R value. I was given to you back on a couple pages ago. Let me just go back and show you. The R value is right here. Okay, so you might want to jot that down at the top of your notes so you have that. Let's go back here. And remember that T has to be in Kelvin, so you have to convert T. So T needs to be in Kelvin, so you have to take your T and you have to go Kelvin equals degrees Celsius plus 273.16. So take your degrees Celsius, add 273.16 to it, apply sig fig rules, and plug in the proper temperature. Please note that this K and this K, or the other K, are not the same. This represents Kelvin temperature, a unit. This represents equilibrium constant. So here's an example 7 where we have pressures. This is just to show you how to write a Kp and use some numbers. So we're going to write an expression for that. And then we're going to do that same thing. We're going to plug in the appropriate atmospheres into the same problem. We should get this answer. Notice I don't have units for any K or Kps, that we just don't put units on those in the final answers. For number 8, this is just practicing writing equations. So here I have written a balanced chemical equation, or I've written an equation based on what it's asking here. Balance it first if necessary, and then write it as it's asking, meaning it says the reduction of black copper 2 oxide, 1 mole of it, so I want this to be 1. I'm reducing this with hydrogen and making copper and water. So here's a K expression. Remember that I'm leaving out. Now, how do I know the states of matter? Well, you're going to have to use the periodic table in my classroom, which is color-coded, or you'll have to look a virtual periodic table up or online periodic table up to see what colors things are, or what states of matter things are. So solids wouldn't be included, and this solid wouldn't be included. So here's a K, here's a Kp. Remember the difference is square brackets versus P. Another example here. Again, I need to write it to the reduction of 1 mole of steam. So I'm reducing 1 mole. So first you'd have to write it, balance it. Both of these happen to already be balanced, so you didn't have to do any adjusting there. All right, example 8. So this is an example where it says calculate Kp for the reaction of 2 moles of gaseous hydrogen chloride with the oxygen to form chlorine and steam. Okay, so I'm given Kp right here, okay, and it wants me to calculate Kp for this circumstance, okay? So we are looking at that same idea here. What do I need to do to this to get 2 moles, the reaction, so that means it has to be a reactant, 2 moles of gaseous hydrogen. Well, it is already reacting hydrogen chloride, so to get 2, though, I'd multiply by 1/2. So I'm keeping it forward, multiplying by 1/2. Remember to apply the rules of K. So because I kept it forward, I didn't put underneath 1. I kept it like it is, but I did raise it to the 1/2 power. That's where I got 5.22. I'd also like you to solve for K. I don't know if our notes say that, but that's what I want to do starting with this year. So we're going to solve for K using that relationship that we established a few moments ago. So here we are beginning that. So here we're going to take the formula and we're going to put Kp in, which we solved. K, here's our ideal gas law constant, or the R constant. 273 Kelvin. I converted my temperature of 450 by adding 273 to 723. Delta N, remember what delta N is? It's the sum of the moles of the products minus the reactants. So this just kind of helps you, this stuff in green, if you can see it okay. I'll kind of move my mouse around in case it's hard to see the colors, but I wrote down how many moles we had of everything, and I got a sum, so that's 5 and 4. Reactants and products, just to remind you. So that's how I got 4, right? Products minus reactants. That's how I got the 4 minus 5, and that's a -1. So you're going to need to do this part first. So I multiply these two. I got this value, then I raised it to the -1/2 power. That's how I got this answer. And then I took 5.22 divided by this and got that answer. Rewatch it if you need to. Anytime. Always pause and rewatch if you need to. All right, for D then, we're looking for K and Kp again. This time we're looking at a slightly different scenario, the reaction of the decomposition of CO2 to form 3 moles of carbon dioxide. So I want to form 3 moles of carbon dioxide and carbon tetrafluoride. So I got to ask myself, what do I need to do? I need to do that. I need to reverse it, and I need to multiply by 3. So I'm looking at forms 3 moles of CO2 as my centerpiece, pardon me. So first thing I did is I took care of getting my K for what it's requesting, because I already had a K of 0.5 up here. So I took it, because I reversed it, I put it underneath 1, raised it to the third. So first you're going to do this bottom part, don't forget. Maybe use a couple set of parentheses depending on your calculator. I got 8. Then I plugged in 8. Remember, this was K that we were given, not Kp this time. So we're going to plug in 8 times this value, right? I converted my 1,000 degrees Celsius into Kelvin. I'm going to do my delta N. If you notice, you have 2, remember you have to reverse this. I didn't write this down, but you'll have to reverse this. So you would have, because you reverse it, these will become your products, but there's 2 of them, and then 2 on the other side. So 2 minus 2 is 0. And you get an 8 when you do that math. Again, check your calculator, make sure that makes sense. Example 9. Okay, so we're looking for K and Kp for the reaction of this. And here we go. And I may have done just Kp this time. I don't know. Let's see. I did both. Okay, so again, it says for this reaction, it's not asking us to modify the reaction anyway, so we're going to be able to use this K straightforward. Or this Kp, apologize, it's Kp for that. Kp straightforward, plugged it in. I looked at my total moles on this side are 2 and 3, so I took products 2 minus 3 -1, did the math, make sure you get these numbers. All right, so the following questions are just going to be examples for you to look at. If you have any questions, don't hesitate to ask. I'm not going to spend time voicing over them. I will just click through them for you so you can see them. These would have been done on a piece of notebook paper or hand out a worksheet that matched up with these. Of course, you know to pause as necessary. Again, just some more practice going over these things. Might suggest, and it's kind of too late to ask that now, but you might have wanted to write them down and then try them and then check. Really kind of up to you. Thank you.